All right. Hi, everyone. As Mark kind of introduced me before, I'm Daniele Gammelli. I'm a postdoc in Marco Pavone's lab in the department of Aa289. And today we'll start to kind of do a quick kind of presentation, short presentation on the way in our lab we are starting to think about how can we leverage foundation models for space autonomy. And the premise in all of this is that it is broadly recognized that we're really living in a kind of golden age for AI and autonomy. And this is motivated by the fact that over the last 2 to 3 years, we have been witnessing kind of a lot of important breakthroughs in a number of different disciplines that are really changing the way we develop like the autonomy stacks. So ranging from effective methods for 3D reconstruction to highly parallelizable simulation to obviously the role of foundation models such as video generation, large language models, vision language models, and so forth. And so kind of with this talk, what we will do is we'll start to kind of take a look about how we are thinking and discuss the opportunities for the role of foundation models in the realm of space robotics specifically. And so we'll do this by dividing this talk in 2 main blocks. The first one will be kind of focusing on how can we leverage techniques that have been developed in the field of foundation models and apply them to space autonomy. The second block will instead focus on how can we use pre-trained foundation models that are out there in a way that is useful across the autonomy stack. But before we get into any of these two blocks, let's briefly introduce and kind of set the stage for what do we even mean by a foundation model, although I'm sure that many of you here are quite familiar with it. So in general, when we refer to a foundation model, we typically mean a model that has been trained on broad data, typically internet scale level, in a self-supervised manner, and that can be adapted to a wide range of downstream tasks. And so examples of this family of methods, as I mentioned before, are video generation models, large language models, vision language models, and so forth. So it's a real family of methods that typically share this underlying assumption. And to this, I would add that typically foundation models really rely on kind of leveraging expressive and scalable neural network architectures, such as transformers or diffusion models. And so kind of with that said, let's get into how can we take techniques that have been developed in the kind of realm of in the literature of foundation models and use them for space robotics. And specifically here, we will be focusing on spacecraft trajectory optimization as a running case study for this block. And so giving some context into spacecraft trajectory optimization in general, the motivation here is that upcoming kind of in-orbit servicing, assembly, manufacturing, and logistics operations will require autonomous rendezvous capabilities. And trajectory optimization is really a key fundamental capability in order to achieve these goals, because at the high level, trajectory optimization formalizes this idea of computing a sequence of states and controls that, broadly speaking, optimize some mission objectives while satisfying constraints that are designed by the user. However, if you look at the kind of field of space robotics and kind of spacecraft autonomy specifically, there is kind of trajectory optimization needs to balance 2 conflicting desiderata. So on the one hand, we have the limitation of space-graded compute, which are kind of orders of magnitude less powerful than kind of Earth-graded compute. And on the other hand, we have these really strict kind of requirements, both in terms of performance that we want to achieve, but especially in terms of safety, because space is in itself like a very risky kind of realm to be dealing with. And when we look at different methods that try to approach trajectory optimization in space, these typically fall within one of 3 main categories, which are, the first one is the closed form methods, which if on one hand are very fast and reliable, on the other they're typically not general purpose because they entail kind of a deep understanding of the problem you're trying to solve and putting them down kind of analytically. The second class is one of numerical optimization, which on the other hand is much more general purpose because it entails restructuring your problem into a mathematical formulation and then feeding this into, let's call it, some black box solver. But on the other hand, these methods are typically much more computationally expensive and therefore goes in contrast with one of the 2 desiderata that we were discussing before. The third cluster, which is much less explored in the case of space autonomy, is the one of learning-based methods, which on the upside can be extremely expressive and computationally efficient compared, for example, to numerical optimization methods. But on the other hand, it's very challenging to enforce strict safety guarantees when we work with learning-based methods. And so kind of in this landscape, kind of a paradigm that emerges as an extremely appealing one, at least in our view, was the one of worm starting. That is, can we leverage learning-based methods to generate fast, potentially also very good initial candidate solutions, and then refine these candidate solutions with numerical optimization, which in turn can guarantee us the safety requirements that are needed. And so if we look at this kind of pictorial image here on the slide, if you imagine finding an optimal trajectory as looking in a high-dimensional parameter space or solution space, learning-based worm starting is this idea of using learning-based methods to generate fast an initial point in this landscape of solutions, which is then fed to a traditional numerical optimizer, which fine-tunes it, maybe converging into a local neighborhood while satisfying the constraints that are needed. And so what we want to do with this work is leverage high-capacity neural networks, namely transformer-based in this case, to provide these high-quality solutions efficiently. And on the other hand, leverage numerical optimization to fine-tune the solution while providing the safety guarantees that we care about. And so when we talk about transformers for control, I think it's just worth setting the stage on how transformers, broadly speaking, work and how can we use them for our purposes. So as many of you know, transformers are essentially the backbone of almost the entirety of large language models today. And at their core, transformers are essentially sequence prediction models. So they take a context, for example, a set of words or tokens, and they are trained to predict the next element in the sequence. And the reason why these are called generative is that because they can generate new text by essentially doing autoregressive prediction. So given some context, the transformer gives us the next element in the sequence. I feed this element in the sequence back in my context, and I repeat this over and over until I get a full paragraph, for example. And in order to switch from transformers for language and natural language processing to control, if you want, simple intuition is that rather than working with tokens and words, we work with states and controls that are still seen as a sequence for what the transformer is concerned, at least. And so what we do here is we propose a method which we call the autonomous rendezvous transformer, or ART for short, which essentially tries to combine optimization-based methods and learning-based methods for trajectory optimization. And the way it does this is by a training time, similarly to how large language models are trained on next element prediction on large corpora of text. ART is trained on a large database of pre-solved trajectories and modeled also as sequences of states and controls, and we try to predict the next element in the sequence. And once trained at inference, we can use ART to generate near optimal or ideally good enough solutions for potentially unseen scenarios. So here on the slide, we have something where given a novel or unseen initial condition and some task specifications, ART can generate a full trajectory for this task, which we then feed to a traditional numerical optimizer for refinement. And worm starting through these methods typically results in faster convergence because the numerical optimization starts ideally in a already good local neighborhood of the solution, while at the same time kind of enhancing the safety guarantees from learning methods with kind of grounded numerical optimization. And what the way we test this is, for example, in hardware, we use a free-flight platform that is just around the block in the Duran building, which essentially simulates kind of space flight through a free-floating robot, the free flyer, on a 3x5 granite table, which essentially simulates this hovering robot in absence of friction, which is similar to kind of space flight. And the way we control a free flyer robot is by controlling the thrusters, or specifically H thrusters, as you can see here on the slide, which are equally positioned around the circumference of the free flyer. And so the goal in this case is to, for example, start from a given initial condition and reach a target position while avoiding the obstacles present in the scene. And so what we observed, and as you can see here on this slide, is that we have the transformer generates pretty fast candidate solution in blue, which is then quickly refined to kind of a safe solution from the optimizer in green. And numerically, we see that this leads to, first of all, shorter compute times, but also a better solution, kind of seen here by the smaller firing time from this platform. And a little bit more quantitatively, we also run this in simulation on, yes, still the free flyer platform, but also on a simulated rendezvous and proximity operation scenario, which are depicted here on the right. So the top one is the same free flyer scenario. The bottom one, on the other hand, is this rendezvous and kind of docking scenario where a service or spacecraft needs to dock, for example, with the International Space Station. And what we look at here quantitatively is the improvement both or potential benefits in terms of cost. So how much better or worse is the solution when we converge? And also how much are we spending in terms of inference time when we compare it to traditional methods? And so now taking a step back, what we've done here, and we're essentially seeing how methods from the literature and foundation model here, specifically transformers trained on large databases, can be used for trajectory optimization in space, so in space robotics, although with some extra care, right? Because in space we care about safety guarantees, and so we have to solve these problems like hallucinations in natural language in order to be able to trust these things. Okay, so that being said, let's move into the second block of this presentation, where rather than taking techniques from the foundation model literature and applying them to space robotics, we try to assess and we take the first steps towards seeing what are the opportunities for pre-trained foundation models like vision language models and applying them throughout the autonomy stack in space robotics. And the premise here is that foundation models, for example, vision language models, possess attributes of intelligence. And this kind of empirically demonstrating strong common sense reasoning and semantic understanding. So here it's like a famous example where given this image on the left, the model is asked like, what is unusual about this image? And here the vision language model kind of correctly recognizes that the weird thing is that there is a man ironing clothes in the middle of the street and attached to a car, right? So this is what we mean by common sense reasoning. And so the question here is how can we better leverage these semantic understanding and common sense reasoning for the purpose of space autonomy? And we have been putting quite some thought into this, and we think that these models have the potential to mitigate three core challenges or at least three core challenges for space robotics, which are scaling ground in the loop or GITL operations, generalizing prior knowledge, and being able to handle multiple sensor modalities. So when we look at the first challenge, that is scaling ground in the loop operations, kind of the current paradigm of space missions is that you have typically there's a tight feedback loop with ground teams of engineers that basically strictly, like closely monitor what is happening. And this is extremely costly and not really scalable. So for example, consider the Perseverance rover on Mars. Kind of the operations of the rover costed around $300 million. And you can probably imagine how this is not scalable in the moment where we want to scale up the number of space missions we do. And with, for example, multi-robot missions, and generally speaking, trying to be more active in the space domain. When talking about generalizing prior knowledge, space is inherently a zero-shot environment, right? So it's understudied. It's typically characterized by unexplored domains. And so what we would like to have is some sort of technique in which we could potentially leverage the learnings and the takeaways we have from previous missions and bring this knowledge to somehow and generalize it to future missions. A provocative example could be learning, kind of leveraging some lessons learned from flying Ingenuity on Mars to the mission on flying like Dragonfly on Titan. And lastly, when looking at multiple sensor modalities, kind of space robots are equipped with a plethora of different sensors. It would be nice to have like a single model that can potentially embed and kind of model all of these modalities at once, and potentially avoiding to have specialized models for each of these modalities, rather being able to use the same model and apply it to various different scenarios. And so when looking at adapting pre-trained foundation models for these purposes, we break it down in two main steps. So the first one is, well, these models, if we want to adapt them to be kind of capable in the space domain, we will have to generate large multimodal data sets that are useful for kind of injecting the knowledge that we need. And we do this by synthetically augmenting extraterrestrial data set, but I will come to this in the next slides. The second thing that we do is, now assuming we have some way of generating this multimodal large data set, we need to fine-tune some sort of open source model for these tasks. And the first steps that we take in this direction is fine-tuning open source vision language models, which we call Space Lava, which is a model that essentially takes this data set, which we compose of tasks like visual question answering, instruction following, question answer that is specifically targeted for space knowledge, but also kind of keeps with it some of the data set on which it was originally trained for, in this case like Lava Instruct, which is useful for co-training, so avoiding a loss in performance and keeping it broadly generable use cases. And the model that we are looking at in this work is indeed a vision language model, so something that takes an input, some image data and some text. It encodes them into a shared latent space, and then it decodes, so the output of this model is also natural language. And this model is then, once it's fine-tuned on all of these tasks, is hopefully able to be useful on a number of downstream tasks. And for the purpose of this presentation, we focus mostly on data curation, and we will see more in the next slide. So again, we're breaking this down in two steps. The first one is we need large informative data sets. And the second one, once we have these data sets, we need to use them with some sort of architecture which we care about. And in this case, we focus on vision language models. So let's look at the first one, which is generating a multimodal data set. So, and this really tries to address what we think is a really important problem in this field, and kind of the space domain in general, which is the scarcity of data. Because this represents like a fundamental challenge in the pursuit of artificial intelligence within the space robotics community. And so what we do here, what kind of the two things that we focus on more is, first of all, since we want to, we say, adapt vision language models in this case, or kind of foundation models, we need some sort of annotation that is in natural language. And this is typically something that is not there in open source data sets. You have maybe a bunch of images and a lot of images, also very high quality labels, but you don't tend to have language annotation for these data sets. And the second thing that we focus on is these models have been trained on internet scale data, so they're broadly knowledgeable. But this data is also earthbound, right? So what we actually want to do is focus its knowledge and really improve its performance when we talk about space-related domains. And so in the context of creating language annotations, indeed, we focus on open source extraterrestrial data sets, such as AI for Mars. It's a famous one, which is shown here on the slide. It's basically images from the Mars surface, which provides some segmentation masks. So it's also high quality labels. So it differentiates between different types of terrains, if we're looking at sand, rock, bedrock, and so forth. And however, these are segmentation masks and not natural language annotations. So what we do is we set up a kind of automated pipeline, which leverages GPT-4, for example, which creates this automated annotation. So what we do in practice is we feed this image that has a segmentation mask together with the ground truth label or thing that we want to leverage from that image. And we ask GPT-4 to automatically generate some sort of textual description related to that task. And so this is one example in which we can automate it, like in an automated way, create large data sets from, in this case, images and segmentation masks that have images and natural language annotations. And the second thing we were talking about is a kind of space-specific knowledge. And so what we do here as again, first steps towards this direction is that we collect 1,000 of the most recent publication in astrophysics from arXiv, and we use GPT-4 to automatically, again, generate a large-scale data set, in this case around 25K, QA pairs. So again, these are two examples, but the kind of main thread connecting them is that we want to achieve these two desiderata, so having natural language annotations and specific space knowledge. But we want to do this in an automated way, and we leverage foundation models itself to create these data sets, which we then can use to adapt foundation models again. And so the result of all of this is a data set, which we refer to here as the Space Lava data set, which is a data set comprised of a number of different tasks that range from visual question answering, space-specific question answers, instruction following, and so forth. And we use this to fine-tune open source vision language models. And the result is indeed our Space Lava model. And we evaluate it on both kind of in-distribution tasks or close to in-distribution tasks, and compare it against, first of all, state-of-the-art models like GPT-4o, but also the pre-trained versions of Lava. So basically saying, we take Lava and we fine-tune it to the space data set. How well does it compare against itself kind of before the fine-tuning? And what we see here is that in distribution tasks for things like scene descriptions or group terrain localization, the Space Lava model actually outperforms the baselines, but also in emergent tasks that are withheld from the training tasks. So these are things, in this case, terrain comparison. So we didn't explicitly train the model on terrain comparison, but we see that because of the training that we did, Space Lava is more capable on doing terrain comparison than the baselines. Yeah.
So what was your metric to assess performance?
Yes, it's a great question. So the way we measured performance here is that we have the score ranging from 0 to 100. And what we do is we feed the output of both the Space Lava, so our model, and the comparison, could be GPT-4o, to GPT-4o that has as its context the ground truth answer. So again, throughout the entire process, we care to have an automated process to have all of the various steps. And so what we're doing is we are feeding kind of a state-of-the-art foundation model with the ground truth answer and the two attempted answer from the two models. And we asked GPT-4o to score these two answers. So again, the takeaway here is that after fine-tuning, we evaluate on in-distribution tasks, so withheld data, but in-distribution tasks, or withheld tasks that are still close to the distribution because it's on the same data. So it's still margin imagery, for example. But then, since we are working with very specialized domain, what we actually care about is also evaluating that we are and making sure that we are not forgetting a lot of the specific kind of knowledge or actually generalist knowledge that these vision language models have. And so here on the right, we evaluate, again, Space Lava against baselines on a far out of distribution tasks that are not related with the space domain necessarily, which here, for example, is a pretty common evaluation benchmark for vision language models. And the takeaway here is that Space Lava, despite this very targeted fine-tuning on space data, is still comparable to its non-fine-tuned counterparts. And lastly, another direction that we evaluate in this space is we've been seeing, until now we've been discussing the use of foundation models, specifically vision language models for data curation, essentially, right? So we are given some image data and we want to generate different kind of textual annotations from that data. But now we want to look into ways in which foundation models could be used within modular autonomy stacks. So if we take a step back, the usual autonomy stack is modular in the sense that we start from perception. This perception is then fed into some sort of planning or decision-making module, which is then fed into a sort of actuation model, which then takes the decisions that I took and actually implements them in practice on the real-world robot. what we try to see here is where in this pipeline can we use foundation models, and where could this facilitate a number of different processes. And the way we do this, kind of the case study we focus on here, is that we demonstrate the use of a foundation model as a high-level path planner and runtime monitor for a lunar rover. So if you can see here from the slide, we are basically dealing with a 3D simulated environment of the lunar surface, where we have a rover and a lander. So these are the two key main players. And the task of this rover is, for example, to reach the lander from its current position. And the way it has to reach the lander is by following some sort of high-level plan that it's been given to it from, say, a ground team. So we have a rover. We hypothesize there is a ground team that gives a high-level plan to this rover, and the rover is then tasked to follow these waypoints. And visually, you can imagine that here the yellow rectangle is the rover, the red is the lander, and the orange rectangles are these candidate waypoints that are given to the rover from the ground team. So where does the foundation model fit in this problem is that we want to use the foundation model as a monitor and kind of evaluator of this candidate path. So the foundation model will receive both the high-level candidate path from the ground team, but also onboard and offboard images. So we will have camera images from the rover, so depicting the current scene around it. And we also have a top-down view that potentially sees a more further away and zoomed out zone of the environment. And so, for example, as a qualitative example here, we had the rover in this condition, and hopefully it's clear from the slide, but it's basically in a situation where it's a moderately visible scene. On the right, there is a really low visibility, and also from the things that we can see, there is kind of rough terrain and uneven regolith. And the candidate path from the ground team is to essentially drive exactly through this kind of poorly lit area, and potentially also risky. And so what we do is we basically feed to the foundation model, in this case just GPT-4, the onboard camera images from the rover, together with this top-down view and a description of the waypoints that we would like to follow. And what we see is that the foundation model, in this case, processes all of these inputs and generates some coherent reasoning, ultimately suggesting an alternative path that is the green one here on the slide, which tries to avoid kind of this unlit region and the kind of hazardous terrain overall. And kind of in closed loop, if we then apply kind of the candidate path, here you can see kind of in the big rectangle on the left, kind of a top-down view of the rover, and then the three kind of frontal cameras on the rover itself. And essentially, what we see here is that I think what is interesting is that we are seeing how foundation models can essentially process these multimodal inputs, which could range from images, textual description of the tasks that we would like to follow, and coherently reason on it and produce some outputs that, in this case, is also quite reasonable. And so this is obviously just a case study, but more broadly, this lunar mobility application represents an instantiation of a broader framework where foundation models could enable multimodal input processing, so combining data from, say, onboard, offboard sensors with mission-specific specifications that are described in natural language, automated reasoning capabilities, right? So we can, yes, parse all of this input, but then do some non-trivial reasoning on top of it. And third, reconfigurable interfaces, because text can be a pretty flexible kind of domain in which to which allows the foundation model to potentially be at different positions within the autonomy stack. And so, taking a step back and linking again to where we started motivated by the breakthroughs that are happening over the last 2-3 years, and we focused on the role of foundation models for space autonomy. And we looked at two different directions. One is directly taking techniques that have been developed in the foundation model literature and applying them to spacecraft trajectory optimization, where specific challenges emerge, like the necessity to kind of strictly tackle the problem of hallucinations. And we solve this, or at least propose a candidate solution through the idea of worm starting. And then we said, rather than only taking the techniques, can we leverage foundation models, pre-trained foundation models in some way that is useful across the autonomy stack? And we've seen the specific example of vision language models for things such as data curation, but also the integration within modular autonomy stacks. And this is my last slide. Thanks.
With training the foundation model for the trajectory generation, how do you deal with like a sim-to-real gap? Because in aerospace, at least, the models for simulation models for vehicles tend to be very complicated, but also very inaccurate compared to complicated real-life models.
So your question, if I understand correctly, is in the first part of the presentation where we train a transformer for trajectory optimization, how do we deal with the gap between kind of the dynamics that we can replicate in simulation and the actual dynamics of... It is a very good question, and I don't think we have like a clear answer that this is the best way to go for it. In some sense, you can, if you have, in space typically you have some idea of the dynamics that you're dealing with. Maybe not all of the aspects are perfectly modeled. But I would say that what you could do in simulation is that you could artificially generate kind of noise in the dynamic or uncertainties in the dynamics that you're simulating. Therefore, rather than asking ourselves, what is the ground truth dynamics and how can I recover in this gap? Maybe one way to see it is, how can I target the training phase in a way that my model is not overfitting for one specific dynamic that I know is wrong, but is rather capable of dealing and slightly adapting to unmodeled effects. Yeah. Yeah.
I'm kind of curious about your comments on these two directions overall, like in comparison for, say, trajectory generation tasks. So the first one is specifically like you train a transformer that can handle the specific trajectory generation task, and the other is kind of embed that into this like text generation, I would say. So what's your comments on like whether people will eventually replace this specific trajectory generation task by embedding that into, say, one of these text generation tasks, or it will just keep, like, this direction will keep thriving instead of, say, like, being kind of, say, like, just classified as a text generation task.
Yeah, so your question, if I kind of reword it, is, do I see these directions to remain separate, or do I foresee something where we have one model that can do text and whatever, but also trajectories? Is this correct? I think, I mean, the second one is an exciting idea, right? So, and I don't see kind of part of the motivation for this is that we think kind of these foundation models can handle very well this multimodality. Now, what this multimodality entails is you know, it's an open question, but it would be very exciting to see, you know, the same model that can take both vision, language, other sensor modalities, and then have as an output also some sort of control. So yes, I see this as potentially the two kind of joining together at some point. Yeah, thank you. Yeah.
So in autonomous vehicles or autonomous robots, they also can crash. So what are you highlighted several differences between the space domain and like ground domain, right? So what are the differences that push you towards not using
It's a good question. So I think that so one big difference between the automotive sector and the space sector is definitely the amount of compute. So you see that in AVs, for example, there is a very fast integration of kind of many of the modules that are originally thought as part of the modular autonomy stack are being replaced by learning-based methods. I think the space domain is much more conservative in that sense, rightly so in some case. And so kind of the way we took a first step in this direction is that we wanted to stay really close with the current strategies that are currently being used for trajectory optimization in space, which typically entail, I mean, what is very popular nowadays is some form of sequential convex programming. So you have a nonlinear model, but you linearize it and you solve iteratively these linearized versions of the problem. And so this is exactly what we do here. So to kind of answer your question is, right now we really focus on trying to stay close from what is considered good practice in the case of space. But I don't see why not. You know, there should be kind of cross-contamination of ideas between the IVs and the space sector.
Is it fair to say that you may allow much slower speeds of decision-making and control rather than in AVM? So you have this, you say, luxury of staying close to computational platforms that already exist for space?
Yeah, so you're saying the compute that...
You don't have to make decisions at 60 miles per hour.
Yeah,
right?
that is, I see, okay.
Therefore, you can stay within, like, MOPS, not FARA-OPS compute platforms.
Yeah, this is one, indeed, depending on the application, of course, but if you look at spacecraft specifically, this is a big distinction.
Thank you.
Yeah, thank you.
Thanks for the talk. I was wondering if you have any thoughts on how, like, foundation models are obviously promising for task planning, but do you have thoughts on how they can be used in, like, system management or, like, vehicle health, like, on monitoring those things on board?
Yeah, it's a great question. Indeed, I didn't mention this during the talk, but kind of some of the other applications that we think could be promising for foundation models, aside from like data curation and like actual high-level path planning, is that it is really exciting to think about all the possible applications across the operations that could benefit from these things. And for example, the like monitoring like the sanity of specific components could be one. Again, I think what really plays an important role is the fact that these, through natural language and being able to handle text or potentially even code, right? These models can potentially monitor what is happening on board, maybe request specific checks, interact with humans in order to say like, do I have green light to run this check or not? Something else could be aid in creating kind of adversarial examples. So if like I'm running like a vision system for like satellite operations, it is very rare to have situations where I have a specific glare on my satellite, but maybe through a vision generation model, I can actually generate some elements of these adversarial examples and probe my system accordingly. So it's a long answer, but in short, definitely, I think there is opportunity there.
You discussed the differences between the computational power of terrestrial compute versus space compute. Is that just an economies of scale problem? The space market isn't large enough to justify the investment in rad hardening the compute, or are there technical limitations that have to be overcome to put more powerful compute in space?
I think it's both. There are definitely also just technical limitations because these compute needs to be hardened and like more resistant to radiations, for example, right? So I think it's a mix of both.
So is there anything particularly annoying that your models aren't capable of doing? Like last time I tried doing things with smaller models like 7 or 13 billion. I didn't even get a lot into the training of those in my specific test, but they would do stupid little things, like they wouldn't follow instructions consistently.
Yeah, I think especially the kind of doubling down on the consistency of these models, right? Especially if a model is not extremely confident about what it's doing, the tendency is that it will start to be very kind of open to changing its answer depending, even with very similar inputs, or like very sensitive to its inputs. Indeed. So I think there needs to be a lot of work to go there. Yeah. So, but yes, like the consistency, being able to solve the task that I'm asking and not going kind of in other directions. Yeah. Yeah, sure.
It seems to me like everybody with robots in the lab ought to be figuring out ways to close the loop with these models. With ROS2 with ROS2 packages and things like that, iron over the problems so that these things can start self-supervising on robotics.
Yeah, yeah.
Your thoughts, sort of a big picture.
Yeah, I mean,
Safety, right? But
yes. There has been some recent work on leveraging like language models specifically for human-robot interface. So if you have like a language model that can generate, highly capable ROS code, for example, you could specify some sort of desired task or outcome that you want to achieve in natural language. This will the model could come up very quickly with some ROS code and interface itself with the robot. And obviously, I agree with you. At the current stage, there needs to be some sort of feedback loop in order to check on the validity. But I think these directions of exploring not only the reasoning capabilities, so can these models solve new problems, but also the interfaces. So can we use these models to rethink a little bit how we interact with robots that could be generalizable across embodiments, for example, or more broadly speaking, help in scaling up operations.